If you're like me, then when you look up at the mountains, you have lots of questions. Like how tall are those mountains? Or what kind of rock are they made out of? Or will that big rock over there fall on my house? Well, it turns out the great polymath, Al-Biruni, had even more questions than me when he looked at the mountains in the 11th century. He was curious enough to answer one of the biggest questions in all of science: how big is the Earth? And he did it with just a mountain and some math. So let's go back to the Islamic Golden Age to learn how a brilliant mind got some very good measurements with some very basic tools. In this episode, we're going to see how a mathematician, astronomer, and physicist did groundbreaking science with nothing but a mountain and some math. Our story begins in the Central Asian region of Khwarazm, which today is split between Uzbekistan and Turkmenistan. There isn't much left of Khwarazm these days, other than a few crumbling walls and the name of its capital city, which now goes by Khiva. But in the 11th century, it was an important center for trade and scholarship, and it was where Abu Rayhan Al-Biruni was born in 973. Like Newton before him, Al-Biruni was a polymath, excelling in many areas of science and mathematics. As a young man, he traveled widely through the Islamic world, including to Iraq, Syria, and Yemen. He became the court astronomer of the Samanids in Greater Khorasan, and later he spent time at the court of the Vizier al-Ma'mun ibn Ahmad al-Bukhari in Nishapur, who was a patron of science. It was here that he began his most famous work, the Kitab al-Surat al-Art, translated into Latin as the Image of the Earth. The book was actually part of a larger work called the Book of Instruction for those who wish to know the measurement of the Earth and its sections and climates. That's a pretty descriptive title, but it doesn't roll off the tongue quite as well as the Image of the Earth. In it, Al-Biruni describes experiments and observations on geography, geology, the properties of light and materials, optics, and astronomy. Now, the reason we're focusing on this book today is that it contains one of the earliest known attempts to determine the circumference of the Earth, or more generally the size of the Earth at its widest point. Today, we know the circumference of the Earth to be about 40,000 kilometers or 25,000 miles, but Al-Biruni's estimate was still remarkably close. He put the size of the Earth at 39,684 kilometers or 24,660 miles. To get that measurement, Al-Biruni used a tool that's still used today to measure the heights of mountains. If you want to find the height of a building, tree, or mountain, then you need only two things: some way to measure angles and a stick, or some other object of known length. Then you can use some trigonometry and simple algebra to get your measurement. This is called a clinometer. There are lots of ways to make a clinometer, but the key thing is that it measures angles from the horizontal. A clinometer uses one or more protractors to tell you how far something is tilted from horizontal. You can buy them online or at any decent hardware store. They come in handy for hanging pictures straight or making sure that your shelves are level. But Al-Biruni didn't have an Amazon account, so he built his own. Al-Biruni's astrolabe consisted of two superimposed dials, a horizontal one for measuring altitudes above the horizon, and a vertical one for measuring angles above the zenith. It's easy to see how such a device could help with navigation, but how could it help you measure the size of the Earth? To find the circumference of the Earth, Al-Biruni needed to know the angle between the horizon and the zenith. At any given location, the horizon is the apparent line where the Earth seems to meet the sky, while the zenith is the point directly above you in the sky. Al-Biruni also knew that the angle between the horizon and the zenith at any given location is half the angle between the observer's latitude and the equator. So if he could somehow measure the angle between the horizon and the zenith, he could double it and add the observer's latitude to get the angle between the horizon and the equator at that place. Since he knew the angle between the horizon and the equator at Baghdad, Al-Biruni just had to get to somewhere else, where the angle was different, measure the difference, and he could work out the circumference of the Earth. He knew that if he went north, the angle would increase because the lines of latitude are closer to the equator. So he set out toward the mountains of the north. Eventually, he reached a spot where the angle between the horizon and the zenith doubled. In other words, he found the angle between the horizon and the equator. But exactly how did he do this? The answer lies in the way Al-Biruni approached his science. His method combined careful observation with mathematical modeling. First, he observed the stars. By watching the stars, he determined the angle between the North Star, or Polaris, and the zenith. This angle, incidentally, is always equal to the observer's latitude. Next, he climbed a tower and measured the angle between the horizon and Polaris. Finally, he went out into the mountains until he could see Polaris at its highest possible altitude. And at this point, he measured the angle between the horizon and Polaris one last time. Using these three angles, he was able to work out the angle between the horizon and the equator, which we'll call x. Let's do a little algebra. Let L be the angle between Polaris and the zenith, P be the angle between the horizon and Polaris from the tower, and H be the angle between the horizon and Polaris from the mountain. We know that L is equal to the observer's latitude. We also know that P minus X equals H, since angle P is the angle between the horizon and Polaris, without any effect of the curvature of the Earth, while angle K is the angle between the horizon and Polaris corrected for the curvature of the Earth. Thus, angle X is the correction factor due to the curvature of the Earth. So to find X, all we need to do is solve the equation P minus X equals H, or X equals P minus H. Now we have an equation that lets us calculate X, the angle between the horizon and the zenith, from our three-angle measurements. And thus we have a way to find the circumference of the Earth. After some algebra and trigonometry, we get this formula, which gives the radius of the Earth. All Al-Biruni had to do was take the length of the arc AB, plug it into the formula along with the angle x, and boom, he had the circumference of the Earth. Now it's time to talk about the arc length. Arc AB is the portion of the Earth's surface between points A and B. When drawing a circle, an arc is the curved line formed by two radii, drawn from the center of the circle to the endpoints of the arc. The length of the arc is the distance along the curve. Al-Biruni figured out the length of the arc by measuring triangles. Here we have three similar triangles, ABC, CDE, and FGH. The ratio of the sides of similar triangles is constant, so DE over AB is equal to GH over BC, and since DE and GH are both diameters, DE times BC over AB is equal to 2 times 1, or 2. So arc length AB is equal to diameter times BC over 2, and that just leaves the question of how to find BC. For that, Al-Biruni used the altitude of Polaris. We can take a gnomon, an object that casts a shadow, and observe the angle between the ground and the tip of its shadow, which in this case is angle F. If angle F is the angle between the horizon and the shadow at noon, then angle E is the angle between the horizon and the sun at noon. Angle E plus angle F is a right angle, so angle E is 90 degrees minus angle F. Now we can use the fact that the tangent of an angle is equal to the opposite side divided by the adjacent side to find BC. We know the angle E, and we know the length of the opposite side, which is the length of the gnomon, so we can just plug in and solve for the adjacent side, BC. Finally, to get the circumference of the Earth, all Al-Biruni had to do was plug the value of arc length AB which he got by measuring triangle ABC, along with the value of x, which he got by measuring the stars into the formula we talked about earlier. So with nothing but a mountain and some math, Al-Biruni managed to get one of the earliest and best estimates of the circumference of the Earth. Although his method had a margin of error of plus or minus 40 kilometers or 25 miles, it was remarkably accurate. Al-Biruni's work demonstrates the power of combining careful observation with mathematical reasoning, and shows how the scientific method helped create one of the most accurate measurements ever taken. At this point, you're probably wondering, what do I need to do to get a Nobel Prize? Well, not to disappoint, but there's no simple answer to that question. But there are millions of scientists working around the world trying to understand the fundamentals of everything, from the smallest particles to the largest galaxies. To understand the world around us and to make new discoveries, we need scientists, and scientists need you. If you want to learn more about the world around you, and maybe even inspire future scientists, then you should consider supporting Brilliant. Thanks for watching this episode. If you liked it, you might also like an episode we did on Rome Ablaze, unearthing the truth of the Great Fur.